Okay, thank you. So I'm happy to be here. So today I'm going to present you my package on turbulence flux estimation, TurbulenceFlux.jl. So this is a package for estimating fluxes at high resolution. So I'm a postdoc at the National Research Institute for Agriculture and Environment in France. So let's start with a bit of context. So we have in our lab we have a flux tower, which is in the northern part of France. So it's part of European-wide ecosystem network of flux towers. So these flux towers are particularly important for understanding the different ecosystems that such as forest, grassland, or wetland. And so it's particularly important to process the measurement of this tower in order to understand how the upper atmosphere exchange matter and energy with the ecosystem below. And behind this exchange, this is the exchange is done by turbulence. So here I just asked a diffusion model to give me some illustration of the turbulence above ecosystems. And so the tricky thing with a flux tower is that you need to only get the turbulent transport that is local to your ecosystem in order to avoid integrating fluxes that come from outside of your ecosystem. So there are standard ways to do this. And one standard way is just to compute the covariance between the vertical wind speed and any scalar, such as gas, such as heat, or such as temperature, or any gas concentration. So the thing is here is that you can see on the gas concentration here that we have some structure in the signal. So we have a low frequency trend that is probably corrupting the signal, and we also have some middle length scales. And if I zoom even more, I can see that I have other structures that are of different size. And the tricky thing is that we have to carefully choose, with this standard approach, we have to carefully choose the average length in order to only capture the turbulent transport. And so this is a kind of a limit to the standard way to estimate fluxes, because by averaging, by using this approach, we do both two things: the separation of scales and the statistical estimation. And if we modify the averaging length, we have an impact on the way we separate the scales, and also an impact on the statistical estimation. And with this approach, we can't get high-resolution estimation of fluxes. So getting high-resolution estimation of fluxes is interesting if we want to get some, for example, the dynamic of the ecosystem, for example, the conductance of forest, for example. So one way to overcome this is first to decompose, then to estimate. So we decompose the signal into different scales with different, according to different frequency band, and then we estimate the fluxes for each frequency band. So the proposed package here is we propose a general framework for decomposing signals in time versus scale coordinates. And so this is something which is known since the 90s for doing this kind of thing. But we integrate also in the package a way to identify the turbulent components in that space. And the way to do this is to use a frame of wavelets with some, since we are doing some estimation of physical quantities, we need to guarantee some energy and correlation conservation. So the frame of wavelets is constrained to have this property. So first we get, here we have the vertical wind speed, here we have the gas concentration. So we make a bunch of convolution with a bank of filters, and then we produce for each frequency band a statistical estimation of the flux in this frequency band. Now I have different fluxes according to different scales, and then I can sum it according to a mask, and the mask here will represent where do I consider that turbulence is present or not. So this approach this is a research work, so we first need to wait for some feedback from the community, but it will be released with the package. So I will start by presenting the goal, and then I will show you some example of result we get. So the goal of this package is to propose a fast and reliable library for doing time versus scale decomposition, because in the literature there was different paper propose different approaches, and I think it will be nice to have something which is general enough and like people can start from this to develop new time scale based approaches for flux estimation. So the features, it will probably change how we compute convolution, but like for now we compute convolution by fast Fourier transform because we have like very big signals, and the wavelets are generated from a generalized Morse wavelet package. So I won't get into wavelets because it's not the purpose of the talk, but this package I developed is already released. And we get some fast enough computation time, so below 1 minute for 24 long fluxes with 20 Hz data. So it represents like approximately 2 million samples signals. And so we also make it differentiable against time averaging on the wavelet parameters, because we wanted to study, for example, the sensitivity of the estimation against the wavelet parameters on the averaging parameters. And also we performed the analysis of the turbulence. So we have a graph structure which is based on graphs and sparse arrays to analyze the turbulence. So in the future, it will be nice to get some new methods for turbulence identification. And as some people that was talking about this, so of course to make it a library, to integrate it in existing standard tools, into existing standard tools. So let's start with a bit an example. So I have some data, so it's a data frame like with some wind velocities, depression, gas concentration. I have my height of measurements, the sampling frequency. Only have two kind of parameters: how I average on our samples on the wavelet parameters. So here the gas concentration, and here the vertical velocity. And if I get the time scale decomposed carbon flux, here I have my time scale carbon flux decomposed in time scale space. And what I can see is at the top here is the small scales, and at the bottom the large scales. And I can see that there is kind of a sweet spot where I have the turbulent transport that carries the carbon across the canopy. So during the night I have a respiration, which is in violet here. And here I have the assimilation, and I get also some structure at the bottom, but I don't know how to integrate it. I don't know if it's part of the turbulence. So we developed the metric that gives us an indication of it, and we can see that it's correlated with the previous pattern I showed you before, that gives us a turbulence mask, and I can use the turbulence mask over the time scale decomposed carbon flux in order to get a time resolved carbon flux with a turbulence mask. So here I have the UC30 is the standard way to do the estimation, and the HRS here is the 10 minutes resolution of our package. So you can see that it correlates well with the standard way to do it, but with higher resolution. And the nice thing is that you can change the length of the averaging length in order to get something which is here less noisy, but you can vary the averaging length. So it's kind of nice. And yeah. So the package will be released hopefully by the end of this summer. And I'm looking also for some contributors. So if you are interested, contact me. Thank you.
Okay, we have time again for a quick question. Or anybody up? Okay, I have a curiosity. So At the beginning, you showed the ICOS location, and your method you said it's general. Have you tried also validation with like the FluxNet locations globally, or?
So we need to have access to the 20 Hz data, so it's not always possible to do this from the ICOS data portal. So for now, I only tried on our tower, so because we have the data. But yeah, we have to test it on actually on higher towers too, because yeah. It's not the same turbulence. And, yeah.
Okay, thank you very much.